Okay, so we're going to now move back into a presentation mode. I'm going to just give you a whirlwind tour of some of the features of MOM6. And by features, I mostly mean parameterization. In fact, I think it's entirely parameterizations. So parameterizations are the, I'm sorry, thank you, take this off. So we have to use parameterizations in GCNs because we don't have the resolution to resolve all the processes we care about. And in fact, much of our science is about how do we actually encapsulate the physics we care about in a model like this, in the sort of models we run for climate. So I'm going to give you a whirlwind tour of the parameterizations we have in MOM6. I'm not going to be entirely comprehensive. I've selected the things I think which are most relevant to the sorts of things we do at GFDL and in AOS. There are quite a few parameterizations I will not mention, but are available. And hopefully, after you've been playing around with the output from the model, you'll be able to figure out how to find some of these things. There is also extensive documentation that Steve pointed to earlier this morning that Kate Hesham has been putting together for us. And there's a lot of stuff in there as well, if I don't mention it here. So I'm going to get started with the horizontal viscosity. And the idea is of these slides is I'm going to just basically name a process, briefly mention what it is, if at all. And there are links, and these slides will be available by Wednesday, linked to from the MOM6 examples wiki. And these links will actually take you to things. So for example, the horizontal viscosity is controlled by a module called MOM or visc. And it has some key parameters in the MOM parameter doc file listed here, such as Laplacian, meaning yes, we can use the Laplacian form of viscosity. You could have biharmonic, which is down there. It's also true in this case. And then the key parameter for the kind of background constant is KH. And again, we're providing in the model output things like the units, what these parameters are, and what the units are, and what their default values are. So again, the MOM parameter doc file is your friend here, just to show you what that would look like in this case. If I click on that link, it takes us to that section of a doc.all file, and it has all of the parameters that are available to do with horizontal viscosity. I'm going to come back to Smagovinsky in a minute. I'm not going to walk you through all these parameters, just saying, this page has a link to that. There is also documentation for many of these modules. Not all of the documentation is complete, but there is a lot of documentation. And here's an example. If I click on that link, this is the documentation for the horizontal viscosity, and you'll see that there's some discussion about what that particular term is doing in the model, and what some of the options are for that module. The viscosity I've only shown you in the slide. KH equals to a constant. That's just a uniform viscosity. We have dynamic viscosities. We have functions of latitude. There's a whole load of options. And the code is very, it matters very much how these things are put together. So there'll be quite a few parameterizations where we've got many, many choices. And you have choices whether you just add things together or you take the max or the min with these things and so on. And so this is an example where we've tried to write out exactly what the model is doing, that there is a fixed viscosity that is a function of all of these terms here that is combined in this particular expression mathematically. And when you're playing around with these things, it is always important to not just trust your input parameters, but to actually look at the output and model. And so a lot of these modules have associated diagnostics. For example, here, actually that's MEKE, I'm sorry, that's terrible. I should be looking for the KH parameter. I've lost it already. Sorry, that's a typo that I've got the wrong link there. But let's see if I can find another one. I'm not sure if I can find it on the spot. Thank you. Where was it? Oh yeah, thank you. There we are. So KH, this is the Laplacian horizontal viscosity, and and there was another one somewhere else here. Biharmonic is just here. AHQ. So these parameters, so these diagnostics are available, listed, linked to from some of these slides. So that's horizontal viscosity. One of the important parameterizations we use in the model a lot is a dynamic viscosity. So I wanted to show you the fact that we can turn that on quite easily. So if I switch to the Smagovinsky viscosity scheme, I don't know what's happening there on the top right. But the Smagovinsky viscosity scheme is something that's become very, very standard practice for us to have something which adds enough viscosity to keep the model stable and close the the momentum equations sufficiently for the model to run stably. And so it has a form of a kind of non-dimensional constant. It's a function of the grid spacing, which is one reason we like it, because if you've got curvilinear grids with variable resolution across the sphere, this kind of helps keep those things, adapt the viscosity as needed. So there's a paper which is linked twice here. I think it's some double cut and paste, did something there. That paper by Griffiths and Hallberg discusses how to do a Smagovinsky in a biharmonic form, and has recommendations for levels of dynamic dissipation to use. So this is again, there's documentation on this, the list of parameters. You set Smagovinsky KH true, you set biharmonic equal to true, not false in this case, and then you have all these parameters associated with that scheme. So that's the horizontal viscosity. Yes. Yeah, so actually what I've linked through to here is I've been linking through to a file called available diags, which the model writes when you run it. And it's something we didn't get to this morning. The model writes out the list of the available diags. Just as it writes out the parameters in their actual state with documentation, it also writes out what diagnostics are available for that configuration. And it writes out in this format. It writes out which module it belongs to, its long name units, and what the style of location. This is kind of CF jargon for whether it's what part of the C grid it's on, or where it is in the vertical. So this is something that has been documented in the MOM6 read the docs page. We didn't go into it in detail, but basically there is a pattern for taking a variable from here and generating a line in the diag table that you can learn and follow. That was Smagovinsky viscosity. The vertical viscosity, very similar. Now it's a different module. It's the module MOM set viscosity. So unfortunately, it doesn't say vertical viscosity, it's just MOM set viscosity. And this is now in the directory source parameterizations vertical. One thing to note here is that this module set viscosity does what it says. It sets the vertical viscosity, but the actual solver lives in another module called the MOM vertfric. And that solver is an implicit backward in time solver, which is something we do for both vertical viscosity and for vertical diffusion, because the grid is able to get to such small scales that we would otherwise be limited in the time step. So we do everything fully implicitly in the vertical for stability reasons. So the solver is basically solving something of the form of this Euler backward fully implicit step. And again, we have a constant value, KV, for kind of a background constant. And there are many other aspects, many other contributions of vertical viscosity, including the bottom drag. There's a bottom boundary layer, and there's a drag coefficient that's part of this MOM set visc module. Other parameters include a lot of other things which I'm not going to explain again here. Could we get a mic on that? Even I didn't quite hear it. So go ahead. I'll repeat it if you say it loudly enough.
Is the background viscosity a lower limit at the model?
This is again one of those things where you have to look at the documentation. It is currently additive, I think. So it's additive, and then other things are added to it, not a minimum. There is, however, another parameter, and I was just going to see if I could find it quickly, which was KV-BBL. Okay, so there are some parameterizations, such as the bottom boundary layer, where we actually have a minimum that is added, that is applied on top of the construction of all of the viscosities. Again, there is a lot of parameters in each of the modules. I can't go through all of them in detail, but okay, so that's the vertical viscosity. And then vertical diffusion, analogous to vertical viscosity, we have an implicit in time Euler backward step for the vertical diffusion because of stability issues. And again, we have documentation on this, which may or may not be. This one is actually not particularly extensive. And there is a lot of parameterizations that contribute to both viscosity and the vertical diffusion. So one of those, so we've just done viscosity, that was diffusion. So one of those, now we're going to get into some of the more interesting physics. One of them is the Jackson-Hallberg leg parameterization, which is a parameterization of shear-driven turbulence. It sets a diffusivity, and through a Prandtl number, sets viscosity. I think it's done in that order. You turn it on with use Jackson Pram, first author here. equals true. And then there's some parameters such as a critical Richardson number and so on. And again, lots of parameters associated with this that are at the detailed level of the parameterization with default, which makes sense based on the papers. But these are all things that are there if you do need to start changing some of these things. So shear dependent viscosity is a very, very important closure in the ocean. We also have a upper boundary layer. We call it the planetary boundary layer in the ocean, meaning this upper planetary boundary layer in this case. And we have something that's been developed at GFDL, the energetically consistent, or the energetic planetary boundary layer, written up in Reichel and Hallberg in 2018. And again, there's a lot of parameters. And this is one of those cases where this is an example where we have some labels for configuring the parameterization, because the parameterization evolved over time in some major ways. So you can essentially select variants of it by these sort of strings. So for example, here he's got a constant form for the M star parameterization, but there were other forms where if you change a string, a whole load of parameters would emerge, and you can set those parameters, et cetera, et cetera. And there are many versions of the configuration of ePBL in our repositories with a kind of the best configuration available in one particular experiment, such as OM4, with later versions on there, being added over time. So again, we've got a set of diagnostics available for this sort of thing, for this sort of parameterization. So I didn't show you the generic diffusivity, which goes into a parameter called KD interface. The diffusivity in the vertical lives at the interfaces in the model in between the layers. And then parameterizations such as ePBL diagnose their additive diffusivity, in this case, KD ePBL. And again, I can't emphasize enough, if you turn on a parameterization, the first thing you should do is look at the diagnostics associated with that parameterization, look to see what happens, because you cannot just assume you turned it on the way you intended to turn it on. So it's important to just go through, dig through, look at the total diffusivity, look at the contribution from ePBL, and you'll be better off for it. Documentation, parameters, again, done all that. So this is the upper boundary layer. Now, this is GFDL's planetary boundary layer. There's another planetary boundary layer available to us to MOM6 through a package called CVMix, which is a community vertical mixing project. And this software was added some time ago in order to access KPP. And KPP is from 1994 larger Lateral review. And again, there's a lot of parameters, and it's available as an alternative to ePBL. Some applications, in particular at NCAR, are using this closure instead of ePBL. And this is an example using a slightly different form of parameters. I'd like to show you this. Here, these parameters, passive, N-smooth, RI crit, von Karman, and so on, those live within a sub-block labeled by KPP percent, and it's closed by a KPP percent. And this is a feature that we haven't used much, but it's something that I'm personally hoping that we start adopting as we start adding more and more features to the model. That's because we're going to run out of names for variables over time as we add more and more features to the model. So we want to start grouping things in ways that make some sense and isolating parameters where it makes sense. Okay, so that's KPP. What are we moving on to next? Okay, related to the surface, we have an opacity scheme. That means how opaque, how is radiation absorbed? It controls how much radiation is absorbed by the ocean. Radiation actually does penetrate over different length scales at different wavelengths into the ocean. And so there are different schemes. There are two main ones which we have are the Menizer and the Morel schemes, and there's a lot of parameters associated with those as well. This matters for the biogeochemistry. This is controlled or affected by the biogeochemistry and does actually matter for things like ENSO. So these schemes, I'm mentioning this because it's associated with the upper boundary layer radiation stratification near the surface. And you will find that you will need this, you'll be using one of these schemes in the couple models, for example. So now, back to diffusion. Another very important parameterization is the representation of mixing driven by internal tide dissipation. There is a module, MOM tidal mixing. And this has quite a few choices within it. We have the silhouette and holes-in schemes coded up, and each of those has their own parameters and own vertical profiles and so on. Again, you would, when you've turned this on within its tide dissipation, you would have to then see what parameters become available. I'll show you some. Again, it has things such as, oh, where are they? Here. Oh, unfortunately, I made this, oh, it is true there. And there are things like the amplitude here, there's kappa I tides. And in fact, this is a tuning constant. This is something that you have to do empirically. You run the model with the scheme turned on, you measure how much work is being done, and then you set this parameter. This is like the amplitude, non-dimensional amplitude that goes into the scheme. Something that we do when we build a new realistic model is one of the sets we take. And it has things to do with topography and so on. So this is another parameterization with lots of internal parameters. The papers to look at here is the MEKE et al. One, which uses this scheme and gives an overview of the scheme's response. There's in the same module, so MOM tidal mixing also provides a parameterization of Lee wave dissipation. And that's again something which you can find the papers for on the top right there. Nick Ocean was a postdoc here and he did some of that work. And again, there's parameters and document diagnostics for that parameterization. Is it, which one should it be? Oh, sorry, my bad. No. But Nick Ocean Ferrari was, yeah, sorry. Yeah, no. Okay, so actually, can we correct that before I post the slides? It'd be nice, thanks. Okay, so that was kind of the most of the mixing wrapped up pretty quickly. The ones I have not explained, but need mentioning, not explained, I haven't been explaining anything really, but what other ones of note that you might encounter in a realistic GCM, double diffusion, and that's controlled from the diabatic driver. The bottom boundary layer was wrapped up in some of those other schemes already. Geothermal heating adds heat at the bottom of the ocean and changes the stability, bit of mixing associated with that. There is, CVMix also has many other closures of which we've currently only added double diffusion, but others are being added by NCAR. So the CVMix package will probably be a way to access other closures which we're not necessarily adding to our current GFDL configurations here. If you are in the traditional isopycnal mode, you wouldn't be able to use either KPP or ePBL, although ePBL may be in time. But what you would use is what's known as a bulk mix layer. That's a completely different parameterization of the boundary layer. And that was used in the gold experiment, for example, the gold model. And then there's also a package called GOTM, which is a kind of collection of many different closures for the ocean turbulence, ocean vertical turbulence. And Brandon actually has, Brandon Weichel has been working towards actually making that something that's available from MOM6 as well. So those are things which are either available now or coming along, and you can browse those at your leisure. Okay, so that's vertical mixing. So now other features of the model. One is tides. So there's actually been some work done with the HIM or GOLD model, where we actually looked at tidal interactions with topography. But tides have been something that have been checked recently. Alan Warcroft, for example, has gone through the tidal code, checked some of the way they work. We can actually add tides. The tidal forcing can be turned on in a global model when you've got the right coordinates and time, and it works. The reason we don't do it in general is because you have to detide your output. So there's a word of warning. We don't have the software at GFDL at this point, I don't think, to do that sort of analysis. So we generally don't turn it on, but it's probably something that we'll be doing moving forward. The regional community want to have tides, so they have some of that software. So the code has the ability to do the forcing. Recently added is the ability to do self-attraction and loading, which is something which we need for doing tides better and evolving ice sheets, I think, as well, right? So self-attraction loading is a feature. Has it actually been accepted, or is it still in development? It's still in development. Yeah. Oh, it's accepted. There we are. So we're getting into a realm which we haven't been able to do before. So that's nice. And now, large-scale ocean models, we don't resolve mesoscale instability. One of the most important parameterizations that's come out of the last mattered for ocean modeling at global scales is the Gent McWilliams parameterization, which we commonly refer to as thickness mixing. I've forgotten to put the reference here. Thickness mixing is a misnomer, is actually isentropic flattening. Sorry, isopycnal flattening, but anyway, the module is called MOM thickness diffusion and is in the source parameterizations lateral direction directory. And this is the form of the closure. It has a bolus transport in the continuity solver, which is the equation you saw twice this morning from Steve and then from Bob. And it is a bolus transport, which is written as a vertical difference of a stream function. Stream function is a function of the model slope. And that slope has a diffusivity constant in it. And that diffusivity has a complex form in MOM6 because we have so many choices for how to set that diffusivity. So that's the thickness diffusivity. And there's a lot of research into what that should be. A few people in this room are working on it. Jenny's been playing around with it. Brenda's been playing around with it. You know, there's a lot of work on what that diffusivity should be, or if even if this is the right form for the closure. Again, lots of parameters. Oh God, I'm doing a bad job with my links today. But the documentation in this one is actually fairly extensive. You'll see that this has got a lot of, I cut and paste some of those equations. But this is one of those modules which has been fairly well documented with a lot of connection between the equations and the parameter lists. So that is one of the more important parameterizations at global scales, global coarse resolution scales. Related to that is the along isopycnal diffusion of traces, known colloquially by many other names. I won't say one of them, but neutral diffusion is one of the ones we do like to use. That is in the module MOM tracer Hor diff, meaning really the lateral diffusion along a coordinate system. And it's now, this one is not in the parameterization directory. This is in SRC tracer. So anything to do with traces is being collected into the tracer subdirectory of the source code. And that's because the model doesn't always have traces. So it's kind of a feature that you can turn on. And so if you're not running a tracer, if you're in stack shallow water mode, there are no traces, there's no parameterizations to use. So source tracer is where these packages live. And this is a case where you can turn on isopycnal mixing. If you're in the LRM, the AL version of the model, you would use neutral diffusion as true, and that would turn on this package. And again, there's some recent papers. Andrew Shao has recently documented this scheme for us. And it's a pretty complicated scheme because we are a general coordinate model, and working out the direction of these neutral surfaces in general coordinates is a lot of work. So that's, I called it along isopycnal mixing, and I know that I'm going to get told off for that, but I did say that there's many names. So now, those thickening mixing coefficients and those tracer mixing coefficients, lateral, have many contributions. One of the schemes which we're actively working on, again, some people in the room working on this, are the mesoscale eddy kinetic energy parameterization we refer to as MEKE. And again, there's documentation extensive to this module. This is actually one of our showpieces for what it should look like. You know, this is end-to-end comprehensive. Everything about the module is actually here. Although I don't know if that's still true because people have been adding stuff to the module. I wonder if they've been adding the documentation properly. But anyway, this module was at one point 100% documented and consistent with the equations there. Let's hope that's still true. Anyway, this is what it should look like. There's a lot of information here, and hopefully it's up to date. So that's the specification of what nominally we want for the diffusivities. And then we've mentioned this paper before. The Hallberg 2013 paper introduced this concept about spatial resolution of the mesoscale. So here is this famous picture, figure 1, which was made in ferret, as was commented earlier. And that's the effective resolution you need, or the precise resolution you need to resolve the deformation scale by 2 grid points, which is not necessarily the same as resolving it. And over here is the diffusivity you get from the MEKE scheme, which I've shown here at 1 degree and 1/4 degree resolutions. These are here the diffusivities you would have at the 1 degree and 1/4 degree resolutions from MEKE modulated by the resolution function. And you can see that the resolution function at the 1/4 degree, which is on the right-hand side here, has the diffusivity set to 0 in many more, in a much larger expanse. Okay, so the 1/4 degree model, in principle, would only have the thickness mixing and tracer mixing happening around here if we were to just use the resolution function like that. So that's a well-documented, I mean, it's a famous paper, and it's all that documentation of how that's done is all part of the same set of modules. But this one, because it's used by both the tracers and the thickness mixing, is actually controlled by a module called MOM lateral mixing coefficients. So one of the things which you'll find in MOM is that, we have this nice idea of kind of setting something up as a self-contained unit. We do that way, and then we discover that some other part of the code wants to use it, and so we end up having to move things around, and so you end up with something that doesn't quite map onto what we wanted. But this is an example of that, where some of the stuff is put into something more generic, even though it's used specifically by horizontal diffusion or horizontal tracer diffusion or horizontal thickness diffusion. Okay, so that was and this title is wrong. This is about the sub-mesoscale parameterization. I'm sorry. So the other very important closure is that of Fox-Kemper et al. And I've got this is absolutely out of date. I'm so sorry. I'm sorry. I'm gonna have to ring this one. The sub-meso parameterization is a parameterization of mixed layer restratification. At least I've got the length here right. So mixed layer restratification is sub-mesoscale instabilities of the mixed layer, and it is in the ocean turns out to be very important for controlling how much heat and other properties get into the ocean. So this is a closure that we have found to be very important, just as at 1 degree in Corsa, the Gent McWilliams closure was very important. Now we're finding that this parameterization is as important for controlling the state of the ocean. And so you will find that this parameterization is generally turned on at any global climate type simulation. Whether we should be using it at all resolutions is something that we're still working on, because this is meant to be a scale aware parameterization, so it should turn itself off at some point. And so why you may not need it at really, really fine resolutions, because it should actually just be turning itself off. Anyway, lots of parameters in there. So that's sub-mesoscale restratification. How are we doing? I think we're close to the end on this, and I'm actually ahead of time, which is great. So other schemes available to you, some of them through the same modules you've already seen, or via various combinations. So geometric is a parameterization from David Marshall's group, and we can reproduce that, I believe, through the MEKE module. QGLETH is a parameterization from Scott Bachman, and has also been implemented via the MEKE module and in the horizontal viscosity routines. Backscatter by Malte Jansen and al. Is something we're currently working on. Talk to Jenny, who's now our local expert on all this stuff. And she's, that's a parameterization of the upscale transfer of energy into the resolved scales from the unresolved scales. And then there is a parameterization that's come out from NCAR to do with how to actually do the lateral processes as you're approaching the upper boundary and lower boundaries of the ocean. There's a sort of tilting of the direction of the fluxes. And so they're referred to as the lateral boundary diffusivity, and that's a module that they've added to try and do that, building on top of some of the work that was done for the neutral diffusion code. And then finally, there is a channel drag, which I think we think is it's a representation of the effect of in a z-coordinate model. You would see a vertical wall, and you would have a drag against that, just because there's a wall there. We've got something similar, but it's because there's a bottom slope in the model, and it's actually the bottom boundary layer being exposed by being tilted. It looks like a sort of lateral drag within a belt. So you've got a slope like this, a bottom boundary layer that's following it, and if you kind of look at what's going on, you've kind of got a kind of local drag against the bottom, but feels like it's lateral, but it's actually the bottom boundary layer. So this is a parameterization of that extra drag you would get by seeing that tilting of the bottom boundary layer. So that's a whirlwind tour of what we have on parameterizations. There are many other features which haven't listed to do with the model. A lot of it's under development, which is one reason for not mentioning it, or advertising it too much right now. But we know we have work with interactions with ice shelves. We have interactions with we have embeddings of the sea ice model within the MOM6, which is an ongoing activity. We have interactions with icebergs, which is an ongoing activity. And then on the other side, we have a lot of work going on to do with either the regional model which we haven't mentioned at all otherwise in this tutorial, just because there's a limit to what we can talk about. And also in the same way that we've set up well, we mentioned it earlier that there's an externals directory. There's biogeochemistry and other kinds of closures involving stochastics, and all those sort of schemes are all packages which have been either self-contained and added or separated in the way we set up the model, so that you can find them elsewhere and actually link to them as we go forward. So I've just given you a whirlwind of what we have in the generic code, but there's actually an awful lot more going on. And if you want to find out more about it, it's something to come and talk to us about. Okay, so I've finished early. I've got 15 minutes to spare, which we can get started on the next one because we can go live. But let's first just see if there's any general questions about what the model can and can't do. Any questions? Go ahead, Bob.
What can't the model do?
So, this model has been developed mostly as a large-scale model. It can be and has been used for process studies, but it's not used, has not been used, can't be used yet for some sorts of process studies, such as non-hydrostatic, that require non-hydrostatic modeling. Although we've been sitting on, the ability to do that, and we've had many proposals about actually doing it. It's just something that doesn't contribute directly to the main goal of what we're doing, which is building a global circulation model. But at some point, we'll give in and non-hydrostatic capabilities will be added. It's just not happening next month. Okay, so what else can't it do? No, you tell me, what can't it do? We are not yet doing, okay, excellent. So we're not yet doing adaptive grid refinement. We're not yet even doing static grid refinement, although that's something that's not always been quite close, because the FMS libraries can do static nested gridding. This is something that we actually wondered about quite a while ago, whether we wanted to have refined resolution in the global model over the important regions, such as the overflows or the deep convection sites. Something that would be a good development activity. There's a related problem, which is gridding the global sphere. So right now we rely, and this is something that Raf spoke about, which is the fact that we have this grid where we have 3 poles. There's 2 poles in the northern hemisphere, 1 pole in the south pole, which gives you a very distorted grid. That's why Canada always reaches the North Pole if you don't plot it properly. But that grid is a tripolar grid that takes advantage of Greenland and Eurasia being where they are. If you wanted to model a past climate, which is not something we do ourselves, the continents wouldn't be in the right place for you to put those poles in the right place. So you would need a better approach to handling the sphere. And so there's been interest, I know, at NCAR, for example, to implementing the cube sphere approach, which has fewer problems with singularities. So a cube sphere approach, I think, is probably going to be materialize as a capability sometime in the next year or so. So that's one thing which we can't do yet, but is probably going to happen. And then unstructured grids is not something we're doing right now, so we're not thinking about it.
Also, waterfalls and cataracts.
Oh, why didn't you tell us about that?
So one of the things we're looking at is the use of MOM6 for the Great Lakes.
Hold it further away from you now.
And the problem with the Great Lakes is Niagara Falls. A little closer.
Just come here to this one.
So Niagara Falls is an extreme example of a non-hydrostatic feature. It turns out that it's actually probably a pretty forgiving non-hydrostatic feature, because it's a critical flow. Everything goes one way. But even going further upstream, there are other cataracts where you get a control point. But using some of the capabilities for, I don't think we mentioned it, subgrid scale topography, we think that we might actually be able to do pretty well. And so that's this ability to actually have the ocean extend past the nominal coastline and upstream into the Great Lakes of the Americas or Africa or something. It could be an interesting capability. Imagine running an ocean model that simulates the Nile River.
So, Sonia, yes? Okay. Well, I was going to follow on things we can and can't do. So if you want to. So the reason we decided not to cover regional is because it's almost an entire model in itself. You know, it's a completely new beast for us. It's still under development. Enrique, would you like to say anything about it to us, or? So yeah, so as whilst Enrique is walking down, for process modeling, we do have the ability to do sponges, and so that's actually been there for a while. But the combination of sponges plus radiation conditions is where regional modeling becomes an art form, which is why you have artists like Enrique.
Fairly. So over the last several years, with a group mostly at Alaska, and yeah, I guess mostly at Alaska, we have turned MOM6 into a regional model. So that involved developing radiation and open boundary conditions. If you're familiar with models like such as ROMS or FECOM, those capabilities are there. They were, I hope, cleverly designed so that in the future you could do some sort of online nesting, two-way capability. That doesn't exist yet, but that's hopefully the long-term plan for that. And we have been successfully running it now in various regional configurations as a high-resolution model going down to 2 to 3 kilometer resolution over the Northwest Atlantic. There's Liz, who left here, she's running California current models. So there's various implementations of that happening. It's a developing activity, but I think it's got a lot of momentum behind it. I don't know if there's any more specific. There's no, you could set that up as for a process study at very high resolution. But yeah, Steve. So the boundary conditions were actually designed to not necessarily be boundary conditions, but sort of interior segments that you could potentially then, so rather than think of it as the boundary of your grid, it's just like a line where you solve a different set of equations. Is that a fair way to put it, Bob? So once you have that capability, you can think of, just drawing a line down the middle of your grid if you want, and just solve radiation conditions on that. They go from one to the other. And some of the boundary conditions that are available also are very simple ones that if you have collocated grids, you could simply copy from one to the next. So that would allow you to do that also very in a simple-minded way. And at some point with Alistair, we drafted on his whiteboard next to his hydrostatic, non-hydrostatic ideas, ways that you might want to do that more efficiently. So that's what's been designed so far has been designed with the idea that sometime down the line we could do two-way nesting, but right now we've only been playing with one-way nesting. And you could extract the boundary conditions from reanalysis or from another larger scale model, whatever the case may be. That is not a problem right now.
Okay, so we are one other follow-up, yes. So question is, repeat the question. The question is, are there plans to do coupled regional? Go ahead.
Yeah, I mean, ultimately, that's where I would like to get to before I retire. The GFDL atmospheric model has nesting capabilities, so they could increase. So FB3, right, can increase the resolution. I think the Weather Service is also very much interested in such things. I think we're actually beginning to go in that direction. I wouldn't say it's there yet, but that's definitely the goal.
So enough of what we can't do. One thing I would like to emphasize about what we can do is we can do idealized models in a way that we haven't been able to do before. So many people have used off-the-shelf models that are very good for high resolution problems, but they nevertheless have some restrictions, such as working in Eulerian coordinates. This model is able to, we're able to turn off the right-hand side of the equations, make the model perfectly adiabatic so that the equations of motion will resort to the stack shallow water equations. And in fact, it's at the heart of the algorithm, as was repeated, said twice today. That actually allows you to do some different, different physics questions about what happens if there is no vertical diabatic processes, which is something we've taken advantage of in a few projects. And it does actually matter. It gives you a different solution than if you are obliged to have diabatic processes in your model just because it's using a different algorithm that has some numerical mixing. So that's one thing we can do really well. Another thing we can't do is QG dynamics, because it is a hyperbolic PDE solver in the primitive equation form. So there is a limit to what you want to do when you talk about using a model like this for idealized simulations. But nevertheless, the fact that this model can take you from an idealized scenario where you're in the limit of stacked shallow water back up to the full equations for a general circulation model gives you a lot of powerful things you can do incrementally, going from something that's purely adiabatic to the full diabatic equations that we use. So I think that the applications for process studies is actually only beginning to open up for us, I think, in that regard. Okay, we've got one question from, so the question is, can we do online Lagrangian particle tracking? And the answer is very soon. There have been a few nascent attempts at this before, and you'll find that when you're building the FMS code, you'll see a package called drifters. We don't use that. There is, however, a package being developed by Spencer Jones, Texas, right? Texas A&M is currently funded by NSF to do this. So there will be something there very soon, yes. And that will be taking advantage of understanding the Lagrangian nature in the vertical. So these particles will not be drifting arbitrarily around in the vertical based on some numerics. It will be actually doing exactly what it needs to do to be perfectly adiabatic. Okay, I'm going to wrap it up now because we need a few minutes to transition over to Raf, who is going to be back to showing you some stuff live. Okay, so thank you very much.